With that, I'd like to introduce Yufei. So Yufei is a fairly new professor in computer science at the University of California, Santa Barbara, and she's won an NSF early career award. Congratulations again for that, Yufei. On this work, a lot of the work you're going to be seeing, for that award. She's also won from the object-oriented programming community. She's won a nice award recently for them for distinguished paper award from them. And she also won she came from North Carolina State for a computer science PhD, where she won the best dissertation award for that. And you'll notice that she, in her bachelor's and master's programs, she did physics. So the reason you're seeing that her work seems to straddle physics and computer science is because that's where she comes from. And so we're very excited to have her talk about some of the challenges in quantum computing engineering. And with that, Yufei, I'll turn it over to you. And again, I'd ask you to please mute except when you're asking a question. And Yufei, again, solicit questions when you're ready for them as you go.
Okay. Thanks for the introduction, and thanks for coming to the talk. So just a little bit more about myself. So I began working on quantum computing after I joined UCSB in 2017 and co-direct the SEAL lab with Dr. Yuan Xie. Okay. So in this talk, I will discuss the challenges and opportunities in quantum computing engineering. I will also introduce my research about how to build high-performance, efficient, and reliable quantum computing systems. In particular, I will discuss the synergy between quantum computing and the classical fields, including programming language, compiler, and computer architecture. So if you have interests in quantum computing, but only have research experience in classical computing, hopefully through this talk, you may get some idea about how to join this new field by leveraging your research experience in the classical field. Quantum computing is already the new race to the moon with national pride. Besides the efforts from academia and dedicated faculty high, many big companies are investigating in quantum computing. Examples include IBM, Google, Microsoft, and Amazon. Many national labs and funding agencies are also very interested in this direction. For example, DARPA recently announced a BA for quantum benchmarking, and NSF also have a special call for quantum interconnect. At high level, many countries have announced their quantum strategies, including in United States, France, and China. So I'm fortunate to work at UCSB. UCSB has been leading the quantum computing research for many years. We have John Martini's group. This group partners with Google and is one of the best groups in superconducting quantum computing. They demonstrate the quantum supremacy in 2019. We also have the Microsoft Station Q on our campus. This site was first established in 2008 and focuses on the theoretical research about topological quantum computing. Recently, the NSF Quantum Foundry was located in UCSB in 2019. This center has a group of faculties from multiple departments working on the next generation of quantum technology. Despite this new quantum gold rush, quantum computing was first proposed in the 1980s, and it has been around for more than 40 years. So we need to review its history before we want to make any new progress. And actually, there have been tremendous of previous efforts, but most of them are focusing on the algorithm side or the device side. On the algorithm side, researchers, especially mathematicians, theoretical physicists, theoretical computer scientists, are trying to develop quantum algorithms that can outperform their classical counterparts in some applications. On the device side, experimental physicists are trying to find physical implementation of qubits with long coherence time, low operation error, easy to control, easy controllability, and good scalability. So we next give some brief introduction to the key achievements from both aspects. So the first, and definitely one of the most important applications of quantum computing, is to simulate quantum systems. Currently, there is no scalable classical algorithms that can accurately simulate a quantum system. However, quantum computer can naturally model quantum systems, and this was also the motivation of Richard Feynman's proposal to build a quantum computer. Over the next 40 years, people have developed quantum algorithms that can simulate various quantum systems. For example, chemistry molecule systems, many-body physics, condensed matter physics, and etc. So it's like the GPU in our daily life. GPU was first invented for graphics, but now GPU can be used for general computing. And we have the same story here for quantum computing. So besides this kind of quantum simulation, and the second, which is a mostly discussed application domain of quantum computing, is cryptography. People find that quantum algorithm can find some hidden algebraic structure that are hard to be discovered on classical computers. In 1994, Peter Shaw published the famous Shaw's algorithm that can efficiently factor a large integer and thus can potentially attack the RSA-based encryption. Shaw's algorithm is also one of the key quantum algorithms which could achieve potentially exponential speedup compared to the counterparts in the classical computing. Okay. Yet, to factor a number that is too large to tackle using classical algorithms, Shaw's algorithm requires thousands of logical qubits and tens of millions of physical qubits once the full quantum fault tolerance is applied. So that's why Shaw's algorithm is promising, but may not be our near-term, may not be feasible for near-term quantum computer. Except from the application in the simulation and the algebraic problems, quantum computing may also accelerate many other applications. One common technique in quantum algorithm design is called the amplitude amplification. Since quantum computing is probabilistic, you can measure different outputs with different probabilities. Amplitude amplification is a technique that can increase the probability of measuring the correct results. One of the most well-known examples is the Gromner's algorithm, which accelerates the general database search. And amplitude amplification is also applied in pattern matching, machine learning, and semi-definite programming. So recent people find that also the previous algorithm has great potential. They may not be suitable for near-term computers, which only has limited computation resources. So they developed a new kind of algorithm called hybrid algorithm, or variational quantum algorithm like VQA, to fully utilize the limited resources on near-term quantum devices. In this algorithm, quantum computer and classical computer work collaboratively. We run a quantum program with parameters on quantum computers, and then the classical computer will optimize these parameters in the quantum program based on the measurement results from the quantum computer. Okay, so this hybrid quantum classical computing paradigm can be applied to applications in many domains, like simulation, optimization, compilation, error correction, and also machine learning. Okay. So now let's talk about the device side. Experimental physics has tried different approaches to implement a qubit with long coherence time, low operation error, and good scalability. The most popular two approaches nowadays are the superconducting qubits and ion trap qubits. Superconducting qubits are fabricated artificial two-level systems. For ion traps, the qubits are implemented with internal energy levels of some neutral ions. There are also other techniques, for example, the photonic systems, which employ the state of photons to implement qubits. The quantum dot is to trap some electrons, to use the spin of the electrons as a qubit. After we have these physical qubits, we need to manipulate these qubits, seeing the implementation of basic set of gates or operations. And we use different kind of control technologies for different qubit technologies. For example, we could use microwave pulses to operate the superconducting qubits. And we will need to use lasers to drive these ions. For photons, we need to use optical instruments like beam splitter, phase shifter, and etc. For quantum dots, we use electro signals. To run practical quantum algorithm, we need many qubits, and then scaling up is an issue that must be resolved. There are different kinds of scaling up solutions developed for different qubit technologies. For example, for superconducting qubits, the qubits are fabricated on a substrate. The I/O wires can be a bottleneck for scaling up, and the 3D integration has been investigated to accommodate more qubits on one substrate. For ion trap, when putting more ions in one trap, the qubit addressability becomes a problem. And one solution is to use multiple traps connected by optical interconnections. To further scale up and connect quantum computers at different kinds of places, the current blueprint is to build a distributed quantum network. It will allow separate quantum devices to communicate via quantum information at a very long distance. The communication infrastructure could rely on the joint of direct photon transmission and repeater-based teleportation. Despite this large amount of efforts from the algorithm and hardware levels, relatively little attention has given to the things in the middle. So recall that in classical computing, we have many technology stacks between the algorithm and the electronic transistors. For quantum computers, we also need those things in the middle. Okay. Actually, today's quantum system is very similar as the classical computers in 1950s, when we just had the first electronic general purpose digital computer. And we mostly write quantum programs as an assembling level. Can you still imagine you want to write a large application using assembling language today? Okay, but we are facing that in quantum computing. And sometimes people need to directly manipulate an analog signals sending to the quantum processors. To push the field forward, we need to have a full stack so that people can write programs, write and use quantum computers more easily. And the quantum programs can be optimized and deployed onto different kinds of quantum hardwares automatically. And further, the hardware resources can be better organized and managed. Okay. So that's why I think we need to pursue the quantum computer engineering. Okay. Here I want to emphasize the potential and possibilities of quantum computer engineering. So our vision is that the convergent study of the classical and quantum fields would lead to transformative scientific and industry progress. For example, in classical quantum computer engineering, we have design automation to design devices of large scale. We also have computer architecture to define the functionality, organization, and implementation of computer systems. And we have compiler and programming language support for program testing, debugging, and optimization. So similarly, after we have the qubit technologies, we should have quantum design automation to help design large-scale quantum devices. Meanwhile, we need to optimize the control of qubits and automatically apply quantum error correction with dedicated control hardware. We also need software engineering and programming language techniques to help develop large-scale quantum application, which would then be automatically compiled and optimized towards different kinds of hardware backends. Draw on these insights, our work have leveraged multiple technology stacks in classical computing to build high performance, efficient, and reliable quantum computing system. We have covered almost everything between algorithm and device, including programming language, compiler, and computer architecture. In the remainder of this talk, I will guide you through our first work on quantum program debugging and testing, and then briefly go through the other works. Due to the time limit, I will only focus on explaining the synergy between the classical fields and quantum computing, plus the special challenges we need to address in this new context. So for interested audience, you can refer to our papers for more technical details. But if you have any high-level questions or like any detailed questions, you can ask in the middle. So first, why are debugging and testing important in the quantum field? It is because programmers living in the classical field would easily make unperceivable mistakes when programming in the quantum field. Bugs has been reported in various open source quantum projects. Here is just a screenshot of a bug report of the IBM's GitHub repository. It is a program for quantum teleportation. This is already one of the simplest quantum programs you could write, which only has 3 qubits and 6 gates. It's like the hello world program in the quantum world, but mistakes can still be made in such a scenario. Obviously, we need testing and debugging tools to facilitate easy programming in the quantum world. So program testing on high level is to match a program state against the expectation from the programmer. Okay, the program state and the expectation from the programmer. One natural thought is to leverage the quantum state tomography, QST, in quantum information processing. So QST has been the cornerstone of quantum state characterization for decades. Yet, a deeper thought would reveal 2 problems of such a QST-based approach. So first, QST is too general and fail to leverage what a programmer's expectation. So in the whole process, we only care about the left-hand side. So the real output from your program, the real program state, but we haven't really leveraged what the programmer have in their mind. Okay, so that is definitely not efficient. If you think about it, we may do too much about this kind of testing because usually the programmer may only have some information about the possible state in your program. Even you give the full characterization of the program state, the programmer may not know whether it is correct or not. So that's why I thought it's too general and maybe gives us too much information. And besides, the tomography itself is very expensive. It asks for repeated generation of the same state and repeated measurements. Another problem with the QST-based approach is it is too specific and doesn't really fulfill all the needs for quantum program testing and debugging. Especially, it doesn't really tell us how to express the expectation at the language level. Okay, so it doesn't really give us an interface to express, to convey our expectation from the programmer's perspective. And the second one is, usually when we do the program testing and debugging, we may want to have a list of sequential checks, okay, at different program points, okay. While the QST, when they do one of the tomography, when they do the tomography for one state, it will destroy that state. So we cannot use that as a state for the following tests. So that is a problem. So for program testing and debugging, for efficiency concern, we may need to have some non-destructive tracking. Okay, so that is a point. Okay, so that's what here just means why I call this approach a left-hand side solution. Okay. To fully leverage what programmers have in mind, we could learn from the classical testing and debugging techniques. In classical programming, users write assertions to convey the expectation. Okay, expectation about the program states at different places in the program. So this kind of assertions. And these assertions are then checked automatically through a set of unit, regression, and integration tests. So if the predicate is satisfied, then pass. If not, then it will abort. Okay.
Yufei?
Yes.
Can I ask you a question here?
Sure.
So, I mean, I think of quantum programming as being in a non-deterministic, a stochastic world that you're working in, right? And so this sounds like a very deterministic, like the programming we've all done, where we sort of put in an input A and expect an output B or something. But this is in a stochastic world, and so A may not lead to B in sort of the classical way. So you got to help me a little bit. If I'm not a quantum guy, so maybe
I think that is a very interesting and very good question. So generally speaking, you are definitely correct. And for this kind of assertion, the problem is even when we have only one input, we need to have multiple executions. That's also one of the problems, like why we care about the efficiency. So very good point, and we will get to that point very soon. Okay, very nice. Okay. So generally speaking, you can see on high level, this kind of classical assertion seems to satisfy our need because we want to leverage the expectation from the programmer, right? So the next question is, like, can we directly leverage what we have in the classical field? And actually the result is no. The answer is no. The reason is the key challenge in design classical assertion and quantum assertion is different, okay? And that means that we could use a similar high-level framework, but we need to develop low-level technologies ourselves. Okay, and here just want to show like what kind of challenges are there for classical and quantum assertions and why they are different. Okay, so in classical assertion, the key is to have a full coverage of all possible program inputs to increase the testing thoroughness, right? And for quantum assertion, it might be fine because we only count one input, right? So most of the input information on many practical quantum algorithms are already encoded in the operation, in the program itself. And we could assume that we just have the trivial input state, all zeros, okay? So the input state encoding problem itself is a very difficult problem and has not yet been solved in quantum field, okay? So it seems that quantum assertion has is better or maybe easier than the classical assertion, but the truth is it's not. Even though it doesn't really have that input level problem or input level challenges, it has its own challenges. And here I just list two of them. So the first one is we need to have strong expressive power, okay? So the language should naturally describe complex quantum state properties that the program may be able to specify. So that language could be different than the traditional classical assertion using Hall logic or anything like that. Okay, so that is the first problem. So we need to define quantum assertions in a quantum way. Okay, so the second one is efficient checking. Okay, so even though we could assume that we only have one input, due to the intrinsic randomness of quantum systems, multiple executions are required to test a quantum program with just one input. Let alone that we need to check multiple assertions on real quantum devices. Okay, so that make efficiency a super important problem. Okay, towards these challenges, we select projection to build our assertion and prove that it satisfies both needs. Okay. So first, I will use several examples to give you some idea about what projection would look like and its expression power. Okay. So first, projection is very powerful. It allows us to specify subspace of any dimensions. Okay. So if you think about it, when we have an n-qubit system, we could have n to the n state space. And the projection can specify subspace with different ranks from 1 to 2 to the n minus 1. Okay. And here, just to give you one example, and here it is a 2-qubit system. Okay. And for this one, when we have this projection P, it means that the correct state must be 0, 0 state. And this P have a rank of 1. If you think about it, all pure state will have this kind of rank of 1. Okay, and the second example is just the same. With this kind of P, the correct state can be the linear combination of 0, 0 and 1, 1. Okay, so it's a mixed state if you think about it, and it has a rank of 2. Okay, so even though projection is very powerful, it allows you to specify any subspace. It still has some it's not it doesn't mean it can specify any states. So for example, so if you have this kind of row with different kind of alpha and beta, so different alpha and beta, you cannot really tell from this kind of projection. And the reason is projection only tells you a subspace, okay, not the detailed, it's not detailed or full characterization of the quantum state. So it's different from the tomography, okay. So our argument is tomography is too strict and too expensive for most of the quantum program testing and debugging. Okay, and projection is just a sweet point, which gives you enough expressive power, but it's still very efficient. Okay. And here I just want to give you some high-level insights behind the efficient checking. So for interested author, our audience, our paper gives 4 theoretical proof. Okay, so why we can like projection is good for efficient checking? So there are the two key insights. So the first one is projective measurement. So under projection measurement, so if you think about it, if rho is the some state you want to check, so as long as that state rho is in our projection space P, then the measurement will not destroy that state. Okay, so that gives you a benefit to check a sequential of assertions, right? Okay, so that is good. So that is one benefit of the projection. But people may ask that in real cases, especially for noise quantum devices, you may have error. So we can never, it's like the float point checking problem, right? So you can never say these two states are exactly the same. So we can only say that this state is approximately is approximately in that subspace or in that subspace to a high possibility. Okay, so in that case, can projection still have this kind of benefits? Okay, so that question can be answered by this kind of proof called gentle measurement with projection. Okay, and gentle measurement with projection just to tell you that, okay, if you have a state which is approximately in P, okay, so for approximately in P means that their trace would be very close to 1. Okay, if they are the same, they are if rho is in P, then the trace will be 1. Okay, and here is larger than 1 minus epsilon, a small amount, a small number. That means that it's approximately in P. Then the good news is the state after the measurement would also be close to its original state. Okay, so you do not need to understand which this part is. You can, it's just the state after the projection. After the measurement, this will be the new state. And D will be a trace distance. You can see the trace distance is still very small, okay, at the level of this epsilon, okay. So, and trace distance also measures the distinguishability of two quantum states, okay. So it tells you that even you have this kind of small error, or like you are working on noisy devices, or like at algorithm level, you can just guarantee that a variable state or a quantum state is approximately in some projection. It's still fine, okay. We will not, after projection, it still works. We do not need to abort, as long as the P is approximate, the rho is approximately in P, okay. And in our paper, we also give theoretical, like theoretically proved assertion checking efficiency in both this kind of exact checking and approximate settings. Okay, so any questions so far? Okay. So like I just give you some high-level insights about why we think projection is a good solution, right? It satisfies the two challenges. It addresses the two challenges we have mentioned in the beginning, right? The expressiveness and also the efficiency. And to facilitate easy usage, we provide a simple language extension to make it easy for programmers to express expectation in using projection. So our language primitive for projection-based assertion is very straightforward. It basically is a projection P, okay, over a set of qubits, Q bar here. Okay, so P is a projection. Q, it could be a subset of qubits in the system, okay? And we could insert multiple assertions and different program locations. And while running on these assertions, we first construct a projection measurement based on P and then perform the measurement. Okay. So that's our language extension.
So Yufei, this is like an assert mechanism that allows you to make sure that things are approximately correct, close enough that you know it's in the right neighborhood at least. Is that the right way to think of it?
Yes, I think we can spot both exact case or the approximate case. And the reason why we want to spot this approximate case is because nowadays for quantum devices, it's not perfect, right? And if you think about it, it's very similar to the classical problem, like when you have a float point, a float point number, right? You cannot say it's exactly the same, but they are approximate the same to some accuracy, right? Yeah, to some precision. And the reason is we cannot have perfect device, right, with unlimited precision.
No, that's a really nice insight. I like that. Yeah.
Okay, great. Okay, so besides the new language primitive and theoretical analysis, we also propose several key transformation techniques to make these assertions executable on real quantum devices. Okay, here I just want to tell you why implementation could be difficult, and you could refer to our paper for our real solutions. Okay, so the key issues here is real-time devices have many physical constraints and can only execute some projection measurements, while like theoretically you can like do any kind of projection measurements. Okay, especially we highlight two constraints here. So the first one is limited measurement basis, and the other one is called dimension mismatch. Okay. So the first one, so what is limited measurement basis? So most quantum computers can only spot measurement along a fixed set of computer bases. Okay, so for example, if M is true, M true is 0, 0, and M false is 1, 1, then we can just measure one qubit to implement this kind of measurement. However, if but if the measurement basis, for example, is in the X basis, the projective measurement cannot be directly implemented, okay? And so we need to have additional unitary transformation to solve this computational basis problem. And there are a lot of complexity in it. But generally, there are also a lot of optimization opportunities. And our paper gave a full coverage for discussion about possible unitary transformation we could apply here, okay, for the real implementation. And the second problem is called dimension mismatch. So what is dimension mismatch? As I told you before, for this kind of projection-based assertion, basically we could define any projection with rank from 1 to like 2 times n minus 1, right? They are all possible. But if you look at real quantum devices, every time we measure one qubit, the space is reduced by half. And then what we have is a 2 to the n minus 1 dimensional space. So it seems that for direct measurement, we can only have this kind of rank 1, rank 2, rank 4 to the rank of 2 minus 2 to the n minus 1. Okay. So for this particular case, you cannot measure it because there is a dimension, the rank dimension mismatch. How to solve this problem? The key idea is we could do assertion combination. Okay, use assertion combination If you think about it, we just use those assertions at these levels as a basis to construct a projection at other of different ranks. Okay, and our paper have a full discussion about possible optimization opportunities in the assertion combinations to solve this kind of dimension mismatch problem. Okay, so the whole idea I want to convey here is, for real devices, there are a lot of practical constraints, and to make it efficient, we need to apply a lot of dirty and kind of dirty and elegant optimizations. Okay, and another optimization we mentioned in the paper is about this kind of local projection. So what does that mean? So here is an example. So for example, like here is a program, and the original assertion we want to do here is here. So we want to do assertion for all qubits, okay? And this would be the program we want to implement. So what is the problem here? So when we have a lot of qubits, so the assertion implementation itself could be very complicated, could be even complicated than the original program. So that is not something we want to have, okay? Especially now we only have this limited quantum devices. So we really want to have something useful, okay? So what kind of trade-offs we could explore? So the idea is we could have some trade-offs between the testing accuracy and the computation overhead, okay? So the idea is we could turn this kind of more complicated assertion into a set of small assertions, okay? And we check this small set of the set of small assertions instead, okay? And this small set of insertions are computed using this kind of local projection of that large assertion, okay? So of course, you could lose some of this testing accuracy, but it's more efficient. Okay, it's like a new tuning law. Okay. And one interesting question you may wonder is, how can we find proper projection-based predicates in practical quantum program? So far we always assume that programmers knows what they have in knows something about this program. They have some expectation in mind. Is that true? Okay. And here I can see, like, actually it is true. A lot of in a lot of cases, the programmers and have some good understanding of this program, of their program. And here is just one example. So for chemistry simulation, and one case is they want to simulate 2 electrons on 4 orbitals. And like you can see, this is one possible like 2 electron state. There are only 2 ones here, right? And this one will be like a 3 electron states, and it should not be valid, right? So the programmer knows what kind of states they can have in the program. And a valid solution should always be in this kind of subspace, okay? And the subspace can like all this kind of 6-dimension, 6 possibilities instead of the total 16-dimension hyperspace, okay? And similar cases about all different kind of symmetries in physics, right? All these kind of symmetries, you can regard them as this kind of subspace, okay? And that would be the expectation programmers have in their mind. So our argument again is the programmers may know something about their program, but may not know the exact result of the final program. Okay, but that part is already useful for quantum debugging and testing. Okay. And here gives you some key takeaways from this paper or from this project. So from high level, this opens up new ways for testing and debugging quantum programs. And it stimulates possible synergy between 2 fields. One field in the classical field, like quantum programming language, and the other one is quantum computing. So at low level, it offers, like the projection offers a sweet point between expressive power and checking efficiency. And we also propose several key transformation techniques to make this assertion executable on real quantum devices. And if you want to know more details, you can refer to our paper. One interesting thing I want to tell you here is recently we found that Honeywell and CQC use our assertion for different purpose. So they use assertion as an error mitigation tool. Okay. And in their experiments, a molecular simulation is performed on an ion trap based on quantum computer. And adding a projection-based assertion in the middle can reduce about the 50% of the error. The reason is quite straightforward, right? The program know like what kind of subspace are there. So if you can eliminate those wrong results during in the middle, right, using this kind of projection, you will have better results at the end, right? So that's a high level idea. Okay. Following the same high level insights, we have also studied the synergy between compiler optimization and quantum computing. Okay. The problem is very similar to its classical counterparts, the register location. Okay. But differs in their key challenges again. Okay. So you will see like we always have some classical counterparts, but we will have some low level difference in the challenges, right? So that's why we could still like inherit the high level framework, but we need to propose new technologies. Okay. In particular, like when we, as a programmer, when we write a quantum program, we always assume that we have ideal device. Where a direct physical qubit interaction is there to enable 2 qubit gates on arbitrary pair of qubits. However, in real devices, for example, like the IBM's 5-qubit chip, direct qubit interactions are only spotted between physical nearby qubits due to the wire routing constraints. Okay, and this is a real like coupling graph of the quantum of the IBM devices. You can see we have much less edges between this kind of physical 2 qubits. Okay, and if you want to conduct a 2-qubit gates between this Q1 or Q4, you cannot do it directly. So that's a problem. Okay, and quantum compiler have to resolve this problem of quantum mapping due to this limited physical qubit connections on chip, and this is an NP problem. Okay. And our work like propose very efficient heuristics for this qubit mapping problem and has already been adopted by IBM's quantum team and some other compilation framework. And here I just want to give you a more detailed example about what is this kind of qubit mapping problem. And suppose we have a real devices where we have 4 qubits connected in a square. Okay. And our program is in the middle, and the current logical qubits to the physical qubits mapping is like this small q are the logical qubits, and the capital Q are the physical qubits. And we have a direct mapping from Q1 to Q1 and Q2 to Q2 in this way. Okay, we can see that the first 3 gates are executable. Because, for example, like between Q1 and Q2, you can see there is an edge between them. So we can directly execute them. And similarly for Q3 and Q4, they have an edge connecting them. So we can execute that gate directly. And similarly for Q2 and Q4, okay. But the problem comes for the first gate. And the first gate is between Q2 and Q3. And there's no edge connecting them. So what shall we do? A possible solution is to insert this kind of swaps. Okay, but how to insert these swaps is a very complicated problem. Okay, and our solution is try to propose a heuristic for this problem. And our key insights is that we could limit our research to these critical swap gates by a deep analysis of the input program. And this significantly reduces the size of the search space, leading to exponential speed up compared to the original heuristic search. And we still have very good results. And the second part is we find that we could, our optimization could be adjusted to different kind of objectives. For example, the number of gates or the circuit depth. Okay, this make our compiler tunable for different kind of devices with different characteristics and optimization projective. So another interesting research we have here is to pursue the synergy between computer architecture and quantum computing. So the high level idea is very similar to the construction of hardware accelerator for ML, for machine learning, okay? Here, so the general idea is if you want to make your quantum device general purpose, then you always have a trade-off between the performance and the yield, okay? So if you have less connection or less qubits, then you can have high yield, but you will have less performance, low performance. If you want to add more connections, then you will have high performance, but low yield. And a good sweet point is, if you limit the kind of application you want to run on your computer, you may achieve both high yield and high performance, okay? And the idea is how to turn, extract this kind of application related information and turn it into a architecture design flow, okay? And our paper have more details. So getting back to this page again. So the synergy between the classical fields and quantum computing could lead to transformative scientific and industry progress for quantum computer engineering. So once you understand the mapping, you could find that there are tremendous opportunities. Okay, just take compiler optimization as an example. We could build compiler for potential multi-core distributed quantum computing. We could also study different intermediate representations for quantum computing. We could devise a set of optimization passes at different abstraction level, and we could design this kind of instruction selection and scheduling problems. And we could even investigate the compiler-based algorithmic auto-tuning to automate the quantum algorithm designs. Okay, so this is our my last slides. So hopefully I have already convinced you that this is a field full of challenges and opportunities. Okay, and here are the following are just some high-level suggestions if you want to join this new field. So the first one is talking to other quantum experts, right? There are people who are already working in this field for many years, right? And you may find that there are not a lot of papers in computer science field, but there are a lot of papers in physics like PIL and Nature, right? And also like people are worried, like whether my research will be obsolete. And the reason is the quantum devices are evolving in a very fast way. But I can tell you like details may, but most of the systematic design may not. And it's very similar to our old days, right? If you think again about the compiler designs, we have different version of CPU, and now we have different version of GPU, right? So we still have the same compilation framework, right? We have some details changed, but the general framework is still the same. And usually like once there is a change, and it also means opportunities, right? Okay. Thank you for attending the talk. So if you have any questions, please ask now. Thank you.
So questions?
Thank you, Yufei. That was a really nice talk. This is Roman Caudillo from Intel. Here at Intel, we're focused on trying to develop silicon spin qubits, and completely agree with your first slide there, where there's a large gap between the algorithms and the hardware. So here we're trying to focus on a whole development of a system. So I really appreciate that slide. Does some of your work also take into account the different control electronics that exist in the middle? For example, we're trying to put some of the control electronics, like a control CMOS chip, in the fridges closer to the quantum devices. And that, of course, lets you scale up quite differently than having racks of AC equipment in the QC labs. Have you looked at some of the differences in implementing algorithms depending on what's in the middle there?
So I'm aware of your work. I think the control logic itself is very important, especially when we want to scale up the quantum devices, right? And the control part could be one bottleneck. And actually, like I think previously, why we want to do the measurement at the end of the quantum algorithm is because of this kind of control problem, right? And your question is like whether the control would different kind of control logic will affect how we want to implement our quantum applications, right? I think one of the issue is, I think it's more like how this kind of control logic will affect how we want to do the combination, right? And we want to ensure we have the feedback. We want to do some kind of this kind of control or measurement in the middle, like whether we want to put into our critical parts. Another part is, for example, what kind of we may want to optimize over the depth of the application. I'm not sure like this is something you are looking for.
Yeah, I guess it's a complex space because you have to take into account not only the different hardware implementations, but the control electronics to each hardware implementation.
Yes. So yes. And I'm also very interested in this kind of control system. And if possible, we could also talk about possible like directions we could work together.
Okay, Roman and Yufei, I can connect you guys.
Great, thank you, Mark.
Sure, thanks, Roman. Berus, go ahead.
Okay. Hi, I was curious about an expression for error that you showed in one of your slides. The expression was epsilon plus square root of epsilon times 1 minus epsilon.
This one?
I forgot which slide number. There was an error expression, epsilon plus square root of epsilon times 1 minus epsilon.
Yes.
And there you stated that the error does not change much, although if epsilon is very small, it seems that this expression gives a much larger number. So for example, if epsilon is 10 to the minus 8, the second term will be roughly 10 to the minus 4.
Okay. Yes, you are definitely correct. Okay, so that's a very good question. So that's why, like, when we do the testing, we have to keep this kind of error in mind. So, and this error will propagate to the next testing cases. And in our paper, we have a full proof, like when you have different, you have multiple assertions, and how this error will propagate to the last state. And one is usually like if you only there are two like error propagation, possible error propagation cases. The first one is when we have multiple assertions, and you have to even add up all these different kind of errors for multiple assertion, and that part like will obey the triangular inequality function. Okay, so you just need to add up for different parts. And another good news actually is, let me find, we have this part. So it's based on the semantics of quantum programs are trace non-increasing. So if you think about it, even though we have an increase of error in that part, so generally speaking, that error will not be huge. And the reason is, if you look at this one, so when we have two state, input state, and the input state, they are very close. And after the same quantum program itself, then the final state will be even closer, usually. So that's the trace non-increasing part of the function. So that's why we need to combine both of them. Yet, but generally speaking, you are correct. So even the epsilon is small, we could have a larger amount, okay, of error. But generally, but that part is still small in practical cases. It's tolerable for a lot of applications.
Okay, Bruce, thank you. You have a follow-up, or are you good? So, okay. So other questions? While we're waiting, I have one for you. Do you think at all about the languages, the programming languages that people will be using to program quantum computers? Is it sensible to talk about, a C program, or a C++ program, or a Python or something like this in the space, or is it just things look different?
Okay, so that's very good question. So nowadays, a lot of like IBM, they have this kind of Python interface, but generally speaking, you are still programming at this kind of gate level or qubit level. And I can take your question to be like whether we could have some high level functions or maybe, right? If you look at nowadays for C or Python, we have a lot of libraries, right? We have this kind of high level constructs. Can we have the same thing in the programming language level? And I can tell you, like for some application, yes, there is already some libraries you can use. For example, for quantum simulation, you do not need to like really write down all these different qubits. Just tell them what kind of electrons like you have and this kind of high level information. But on the other side, so your question could be interpreted as for compiler optimization. Do we need to do all the optimization at the gate level? It's like we are doing optimization at the instruction level. Can we create some intermediate representations? And the general answer I can tell you is it's possible, especially for some application domain. And we could create some intermediate representation and let our compiler to do the optimization at a really relatively high level. And the good part is when we are doing the optimization at a high level compared to the gates, usually we have larger optimization opportunities. And we could have this kind of large scope when we do the optimization. Usually it gives us much better optimization results. Okay, so.
Yeah, I mean, it sort of like begs the question about like what RTL looks like in this world, and what, you know, all of those, I mean, all of those kind of design languages and all of that sort of stuff too, right?
Okay, yes. And I think for RTL, another question is like, well, when we want to design our quantum devices, can we describe this kind of quantum devices, use this kind of hardware description language as we have used in the classical field? So I think that is another possible synergy between the classical field and quantum computing. So generally speaking, I feel that they are full of these opportunities. So the key is we want to find the key challenges in the new context, right? And in my mind, so my vision is a convergent study between the classical field and the quantum field will make things much faster and much better.
It seems like some kind of breakthrough is needed there or something.
Yes,
you know,
yes. So we need to have people like who are experts in the classical field, but they also have interest in the quantum field, and we have to educate them about what kind of problems we want to have. So that's why I feel like people in these two fields should talk more with each other.
Great. Okay. So we're a minute after the hour, but it's okay if we go a few minutes still, if there's still further questions, you know, from any of the other eminent participants here. Any other questions for Yufei? With that, I think we will let you go, but it was really great, Yufei. Thank you so much. It was really a wonderful talk. Thank you so much, and appreciate your efforts, and thanks for the good questions, Roman and Beruz and others. And we'll see you all on June 3rd, unless something pops up on the calendar before then. We'll see you on June 3rd for Galen Moody's talk. Thanks again, everybody, and stay well and safe.
Bye-bye.
Thanks, Yufei.
Thanks, Yufei. Thank you, Mark.